everyone. Thanks for joining in. Yeah, so this is going to be talk about our work on secure multiparty computation in the post-quantum setting. Um, yeah, I'll have a lot to say. So, funnily enough, this has appeared more recently, but it's an older work. It's been doing the rounds. So I guess I should start with some caveats because this is going to be in this area of like multiparty computation, and it assumes a lot of context. And I will keep it hopefully very friendly towards people who have not seen a lot of this area before. And yeah, please pitch in with questions if you need. Right. So what is secure multi-party computation? So the problem is about multiple parties, as you can imagine. It's really a distributed protocol. So you have different parties which have their own separate inputs, which they want to keep secret. And you want to ideally compute a function over all of these inputs. And so these parties will communicate amongst each other, and they will exchange messages. And at the end of such a protocol, you really want this function over the joint inputs to be computed. And one requirement is, of course, you want it to be computed correctly, meaning you do not make a mistake. And the second constraint we sort of assume is privacy, meaning that really nothing unnecessary should leak about your private input. Meaning that if you want, to share your health data, you don't want necessarily your banking details to be published, right? So, the algorithm should access and reveal your data judiciously, right? So, what is the security requirement? As you can imagine, this scenario can be quite general, and so our security definition is also very broad, and it's instanced in different ways. So the basic paradigm that we follow in MPC is the following. So you have your protocol, and you also imagine alongside it this sort of ideal world where all the parties have their inputs, and we assume that there exists some ideal trusted third party which does this magical thing of just taking in everybody's private inputs and computing the function for them and then sending it out. The security requirement is as follows. So suppose you have a party that's sort of cheating or behaving maliciously in the actual protocol. You want to show that there exists a so-called simulator S, which runs in this sort of ideal world that we have defined alongside this. And the simulator S can act as a malicious party in the ideal execution and manage to reproduce the outcome that this cheating party in the real protocol manages to perform. So if you denote these variables, denote these outcomes as random variables on the inputs, which they are, so we call them the real world variable and the ideal world variable, then the simulator is really actually looking at this malicious party, which creates this real scenario and reproducing an ideal world that is identical. And usually we'll mean computationally identical, meaning that there might be a difference statistically, but efficient algorithms cannot tell these apart. So I'll pause briefly for questions about the setting. Okay, great. Now, as you can imagine, this has a lot.
Rohit, sorry, before you go on, so on the previous slide, here we are looking at the, so when you write real as a function of the inputs, we are looking at all of the outputs. So real basically is looking at the joint variable of all the outputs of the parties.
All the outputs. And actually, you have to be a little bit more specific in terms of you're looking, since you're simulating for this one party that might be cheating, you're really looking at their view of the protocol. So typically, very specifically, this includes all the internal inputs and coins this party may have, and like the messages and things like that they will receive during the protocol that will create the real thing. And as you can imagine, the simulators function operationally is to generate all these fake messages and communication that this party will typically see in the course of a protocol indistinguishably.
But
does it make sense?
So you're saying you don't. I mean, I remember reading things about this and back when I was looking at it. So here the output, you're saying it's not necessary to look at the joint output distribution of all the parties. It suffices to look at just the output distribution of the malicious party. Because I remember there being a caveat that you have to look at the joint thing in general. Is that not true?
Yes. So typically, because you can corrupt multiple parties and things like that.
So that is
So
fine.
so that is fine. And the other thing is, for honest parties, it's also like a lot easier to simulate things. So sometimes you can move between these two notions. So I think
No, I
you
meant to ask that. Sorry. Before you go on, just to quickly clarify.
yeah.
So the I thought you had to produce even when you're producing the simulator. I
Yes.
thought we wanted to construct a simulator such that the joint output of the honest and the malicious party in the real world is indistinguishable from that of the ideal world. And I thought
Yeah.
it was
So
important to consider the joint distribution.
you're
But are
right.
you
You're right.
saying that it is not necessary to consider the joint? It's enough to consider just
No, these
the
things can
distribution.
be quite different, but typically it's not too hard to do the
I'll go
simulation for
from
the
one. I see.
yeah.
That's what you meant.
So
Okay, got it.
yes.
Thank you. Sorry.
Yeah.
Sorry, I'm a bit slow. Thank you.
Yeah. No. This is actually very confusing, and there's no good overview of these things. In any case, so yeah. So alluding to the previous thing, you can look at many parameters for such protocols. So you can consider things such as, round complexity, which is how many times do you have to talk to one another. Communication complexity, how big are your messages? How are you allowed to perform your corruptions? Like, can you come in and sort of make a party malicious in the middle of a protocol? Can you allow them to behave arbitrarily and not follow the protocol, or do you have to sort of do that to the letter? And, when can parties stop and refuse to respond and things like that? So different protocols will offer you a different set of guarantees along each of these things. So some protocols may be theoretical, they might have very good communication complexity, but they might not be able to deal with things like bots and things like that. Especially in practice, these things end up mattering a lot. And additionally, you can make simplifying assumptions. So these are often modeling assumptions, and these can include various kinds of things. So you can assume that there's some trusted ideal party. This is not, circular. So by this, I mean, basically, you idealize some component of your computation, meaning you're computing maybe some complicated, large distributed thing, and you take some subpart, some sub-function, and you assume that there's some ideal functionality that does that for you. And you can use maybe, like, this can be important in many ways. Maybe you can use this idea for composition. Maybe you take one protocol that achieves this guarantee for the simpler function and use it inside a larger protocol and things like that. You can assume that certain primitives or cryptographic functionalities are carried out ideally, which again is helpful for composition. You can assume shared randomness or correlations of any specific kind that you might want. You can also think about certain baseline fraction of honest parties, meaning that you assume that you always start with, let's say, a majority of honest parties and things like that. And this is actually very useful because there's a whole class of information theoretic MPC protocols that make essentially only this assumption and nothing else. Uh, um, and also you can consider other strengthenings, such as you allow the simulator to be more powerful and things of that nature. So for our specific purposes, we will look at the following settings.
Rohit,
So
before you go on,
oh,
can I
yes,
ask another small
yeah,
question? I have two quick questions. So one was that I was still thinking about the model, the simulation thing that you had mentioned.
yes,
And
let me
I
go back.
remember reading that whether you require the transcript to match
Mhm.
or you require the output to match, that at least in the bipartite setting, I thought it was equivalent because, if you match the transcript, of course, it'll also match the output. And if you only require the output to match, then you can always consider a malicious party that outputs the transcript itself. So these notions, I think,
Exactly.
in the bipartite setting were equivalent. Is it also the case in the multipartite setting, or does
Yes,
something subtle
because
happens? Okay.
I think the argument you're making will also go through because you also allow
Okay.
multiple corruptions and things like that, right? So
Yes.
usually you do not
Okay.
make a difference. And typically we want to consider like equalities of the transcript and so on. Yeah.
Right.
This is
And the other thing was there was some, there's a notion of sequential composition and universal composition because, like, the parallel and
yes.
sequential thing. Does it appear
Yes.
here or will it appear later in the
So
definition?
I will not really talk about composition much. A very important distinction. So sequential composition typically just means yeah, you're composing multiple protocols sequentially, and this is usually kosher for most protocols. That's a very low requirement. Things like parallel composition and universal composition, we'll see specialized versions of this in the talk, but universal composition is understood usually to be the strongest such notion. It's very strong, but it's also very painstaking to prove. So typically, the notion is quite involved. It sort of sees the adversary as this environment that can coordinate
Right,
everything in the ideal world.
right.
Uh,
So we're not
and
doing that here in this
well,
talk.
no, I will consider
Okay,
mostly
okay,
just sequential composable protocols. And
okay, okay.
yeah, this is also called the standalone setting typically because you're not looking at
Right,
any
right.
kind of compositional
Exactly,
functionality. And
exactly,
but
exactly.
we will rely on tools that came from the UC world, and I will point this out when I. So there's some compiler that we'll use to get the overall protocol that works in the UC setting. And I mean,
Okay,
again, that's one illustration of the
makes
strength of this
sense.
setting because I can use it anywhere I want. Yeah,
Thank you.
cool. So yeah. So what assumptions do we want? We'll want this thing called oblivious transfer, which I'll illustrate in a second. This is very widely seen as this asymmetric public key sort of assumption because it's implied by public key crypto and is also roughly equivalent to it. This is a necessary assumption. This is shown in many early classical works. Even for classical MPC, you want essentially implies OT. And very often, this is also a sufficient assumption. So basically, you can think of the oblivious transfer as like kind of a specific correlation that gives you this framework that allows you to do MPC. So how does the OT actually work? It involves two parties, the sender, which is on the left. Yes.
Start with the description of OT. Just this a quick question about the relation to public key encryption.
Yes.
So
Yes.
is it because I thought OT implied private key, like you can exchange, like key exchange, right? Basically, I thought oblivious transfer implies key
Yes.
exchange, but
Exactly.
there's like a number of rounds issue, right?
It,
Because so
yes.
it's not
That's
strictly equivalent, right? Is that why you're saying it's essentially the same?
It's
Is that
strictly equivalent.
okay?
Yeah, exactly. The other caveat is encryption by itself is like not interactive, right? So it's hard to like
Exactly.
directly compare also.
Okay, got
Yes.
it. So interaction is
Yeah.
the main thing. Okay,
Yes.
thank you.
Yes. Yeah. So cool. So let's define oblivious transfer. So you have the sender. The sender has some information. Let's say it has two strings, and consider it kind of like an information seller. It has these two strings. You're allowed to pick only one, but you don't want to tell which one you want to pick. So you have your choice as the receiver. So this is denoted by this bit P. And the outcome I want at the end of this protocol is that I have the choice of message that I want, either M0 or M1, and the sender knows nothing about this. This is why it's called oblivious. Yeah. Great. So typically what other tools you would need to construct an MPC protocol is things like commitments and zero knowledge proofs and so on. But these things generically they can come from one-way functions, so you don't worry too much about them. Really, the specialized gadget you typically need is this oblivious transfer. Right. Information theoretic protocols, which I mentioned earlier as well, of course, use no computation assumptions, but there you're relying heavily on these requirements about a certain fraction of honest parties and things like that to get by.
Rohit, sorry. So what is the status of zero knowledge arguments? Like, do we know that they can be built from one-way functions like entirely? Because I thought there was some like in the post-quantum setting. Classically, I know that this is fine, but
Yes, so I
in the
think
post-quantum setting, there was like some inverse polynomial issue, right? Or is it?
yes. So that will be
Oh.
important for us. So I will cover that, I think, in a few
I
slides.
see. Okay. Sorry, please carry on.
Yeah. So this is just to give a sense of sort of the ingredients that we need for the protocol. And in terms of security assumptions, typically security can cover 3 different flavors, as is typical in crypto. One is computational, which means you want to be secure against polynomial time, either classical or quantum computers. Statistical with security, which is stronger. And sometimes actually you can also get perfect security. For these information theoretic protocols, actually, it's often commonplace to realize perfect security. So the requirements are sometimes more stringent in terms of number of honest parties and so on. But you can get this, which is kind of interesting. For our purposes, we will focus on computational security. And since we are in the post-quantum setting, we will consider security against polynomial quantum attackers. Great. So let's look at what's known in the classical world. So here, to recap what was said before, I will be looking at this thing called the plain model, meaning that I'm not making any modeling assumptions as such. I will consider assumptions which have polynomial strength security. I will be looking at black box simulation, which means that the simulator itself does not need anything more than black box access to the other parties, to the protocol, and so on. And I am looking at standalone, which is sequentially composable, etc., and computational security. The first seminal work of Goldreich, Mikhaili, and Wigderson gave you this construction based on zero-knowledge proofs. There were some information theoretic protocols. And in the 2010s, actually, we started seeing the first constant round constructions just from one-way functions. This is very interesting. And we will be looking at a little bit at the framework they sort of follow. And people kept improving these things. So in 2016, there was this work that gave you a lower bound on round complexity for black box simulation. And also gave you a 6-round protocol based on the LW assumption. And
Rohit,
finally,
sorry, so I'm a bit surprised. So in the 2011, so the third bullet point,
yes,
it says first constant round from one-way function. So clearly it must be using OT, right? Somewhere. Or you're saying that the entire construction is only using one-way functions.
right. So let me recall.
Because we don't think we can construct OT, right, from one-way functions. So it's very surprising that your third bullet point is.
So it really comes down to round complexity.
But I thought even in general you cannot, even with polynomial rounds of interaction, I thought you couldn't do oblivious transfer from one-way functions, right? There's a black box separation, I'm guessing. Like in the random walk. No.
Right, and I think that might be the thing. So yeah, I'll have to recheck this because I don't quite recall.
Yeah, maybe something about adding an assumption to reduce the number of rounds in addition to whatever assumptions the prior thing had. Maybe it's something of that nature.
Right. So these were essentially, I think, maybe I meant non-malleable commitments here. So yeah, maybe this includes OT as well. So yeah, sorry for the confusion. I think I'll have to clear this up.
No worries. Carry on. Yeah, it's not an
Yeah.
important point. I was just curious. Sorry. Yeah.
No. Thank you for pointing it out. So okay, so you have at the end, really, you have these very, very round compact protocols. And essentially, you can do as good as your OT. And sometimes if you make stronger assumptions about simulation and things like that, you can do even 3 rounds and so on. So this is very well understood in the classical setting. What's known in the quantum setting? And here we'll allude to some of these rules.
Sorry,
Yeah.
Rohit, I missed. So the lower bound was for what? How many rounds? Was it 4 rounds? Like, is it optimal or?
Yeah, 4 rounds I think is optimal under polynomial strength assumptions.
Oh wow, okay.
Yeah. Because
what do you
there's
mean by
some
polynomial strength assumption? What does that mean? Like,
So whatever hardness assumption I'm making gives you security against polytime attackers, not
I see that
sub-exposed
way.
security
Okay.
and things like
Okay.
yeah.
Got it.
If you have that, you can do better, yeah.
I see.
Right. So okay, so let's turn to the quantum world. So what do we know? So there was this work in 2021 that showed, I think this by Alex Grillo, Amit Agarwal, yeah, some subset of, yeah, Dakshita Khurana. There's a post-quantum and constant round construction of an MPC protocol in the standalone model. And it's non-black box. In fact, it's highly non-black box, and it uses this specialized technique, which depends on this very particular form of multi-key fully homomorphic encryption, which is, in my opinion, a pretty strong assumption. But this was kind of the limit. And so there was concurrently a lot of exciting work on like these sort of partly quantum MPC protocols based
Rohit, sorry,
on,
did
yes,
we know how to instantiate multi-key FHE?
they have
Oh,
this thing based on LWE. So
like the usual
I'm not,
hardness, or is it like sub-X? Okay.
you need a little bit more hardness. And I think it's based on this template from there was, I think, this paper in 2016 by Dodis and others
Oh,
about
okay.
this spooky FHE where they use these sort of they
Right,
realize
right.
some sort of
You can generate
additive
stronger
homomorphism,
correlations,
yeah,
right,
multi-key
across different
FHE.
keys.
Yeah, so I think they're essentially relying on that kind of thing. So I think you might need some slight, like
Oh,
non-standard assumption in there.
interesting. I see. Okay, thank you. Okay.
Yeah, so that was what I recall from them. And yeah, so like I was talking about, in terms of protocol with classical communication, you had this protocol from 2021, and then you had these other protocols which get OT from quantum commitments. So they, in particular, cross this symmetric key to public key barrier, so to speak, by using this sort of BBR-based protocols. And these, however, are not constant rounds, and they're not also classical communication. And I think they're also, uh, they're not black box exactly. So
What is the
while,
BBR template? Sorry.
so it's based on,
Is it like initials of authors, or is it?
yeah, it's this thing that's used
Okay.
in, uh,
It's fine. No, I don't.
yeah. So it's to do with what's the word? Wiesner state-based things.
Got it.
Yeah. So there's the thing from QKD, I think.
Right.
So anyway, the pathway is left open for getting the kind of black box protocol that I've been discussing so far in constant rounds. That's what you would think, except I think you were looking at this result. There's this impossibility result in the setting of post-quantum cryptography, which says that unless you have NP and BPP, there is no post-quantum black box zero knowledge protocol for all of NP that works in constant rounds.
So black box zero knowledge basically means you assume that you can run zero knowledge as an ideal functionality, and everything else is information theoretic. Is that what it means? Or?
No, it just means that your zero knowledge protocol is not using any component like any commitment or one-way function in a black box manner. So this is, I think, in the constructional sense. Yeah, so you don't have a post-quantum black box zero knowledge protocol in constant rounds for these things, unless very surprisingly NP is in BPP. So you also don't have, as a consequence, 2PC or MPC protocols, because all of these things will imply zero knowledge. So this kind of shatters our hopes because there's this obvious barrier. So what can we do about it? So post-quantum black box MPC, as I said, you have this definition with the real and ideal world. One thing to do is not stick to constant rounds. to get a protocol that realizes this. The other is to move to this notion of what we call epsilon-based simulation security, where you have this inverse polynomial error parameter epsilon, and your simulation may depend on this error parameter in the sense of a p-test to give you the security. So this is not quite giving you the standard notion where this computational distance is just negligible, but you can do almost as good by allowing your simulator to time in inverse polynomial epsilon. You can realize epsilon security. And this is a pathway that has been followed by some of my co-authors also, that looks at these things. So in this work from 2021, you have a black box post-quantum epsilon zero knowledge protocol in constant rounds. So this just bypasses the negative result I showed earlier. And this was extended to a black box post-quantum epsilon 2PC and epsilon simulatable extractable commitments in constant rounds in a follow-up work, but no MPC as of yet. So this leads nicely in our results. Yes.
Rohit, could you say a bit more about how one should think about this epsilon security?
Yes. So
in the sense that, yeah, like how does, yeah, like what is the intuition? Like how should one, yeah.
You will kind of see where this 1 over epsilon comes from. And really, this is saying that, okay, maybe there's no generic method so that you can simulate up to arbitrary negligible factors, right? But you're saying
But
if you give
in practice, sorry, please go ahead.
No, yeah, please go ahead.
Oh, I was just wondering, so I'm guessing this notion is enough, right, for practical purposes, I'm guessing.
Yeah, I mean,
so I just wanted to understand how you think about that. Like
so the good thing
it
about
seems okay.
not worrying about this epsilon is like you use and forget, right? So if you have shown the simulator that gives you negligibly close simulation, you kind of don't have to worry about things. Now in this epsilon based setting, you're sort of carrying over this epsilon, right? So maybe you're running multiple things together, and then maybe your error parameters may have certain dependencies, and then you need to think slightly more carefully about what epsilon you can. And so you have to work backwards from that.
So what if so let's do the simple setting, right? So suppose it's a standalone security and just running this protocol. Do I need to know something about the adversaries to set the epsilon, or how do I think about it?
So your epsilon will be, let's say, if you're doing some, this is very, very far out because obviously these things typically are not used in practice, right? But if you're thinking along these lines, maybe you're working the concrete security setting, so you may have some parameters. So you're allowing the adversary certain runtime and a certain success probability, and combining these two numbers together, you may come up with some notion of epsilon, right? So
you're somehow assuming, like intuitively, we're thinking that it's not, because polynomial is essentially unbounded in a sense, right? Because there's no strict bound. So you're saying if you somehow had like a fixed polynomial for the runtime of the adversary, then you could appropriately choose epsilon so that they couldn't possibly recover. Is that the idea?
In some sense, you can think of it as advice, essentially, right? So you're saying that if you tell me a number beforehand, I can sort of commit to it and give you that level of security. I can't handle all possible polynomials.
I see. Okay.
Yeah.
Okay.
So it literally is a p-test in the sense that you give me whatever epsilon you want, that is inverse polynomial. I will build you a simulator that takes correspondingly high runtime. Yeah.
Got it. Thank you.
Yeah. And it will come out very naturally
and just to make sure this epsilon, I guess, appears in the protocol as well, right?
Yes.
For every epsilon, there's a different. Okay. Makes sense.
Yes. So it will come out in the runtime of some gadget that we'll use. And it stems exactly from that. Okay. So yeah, turning to our results, we have two different MPC protocols. So the first one has all of these properties, namely it has post-quantum security, by which I mean it's secure against quantum polynomial time attackers, offers this epsilon simulation guarantee that we talked about, is black box in construction and also in simulation, takes only constant rounds. And it's also good to stress that this involves only modest assumptions. So one-way functions plus polynomially hard LWE, which we need to realize the OT component in the post-quantum setting. And there's a lot of primitives. As in, this is not a very limiting set of assumptions. Um, and the consequence is it puts the post-quantum MPC setting on even footing with the classical setting if you are willing to tolerate epsilon simulation, which we said is clearly different, right? On the other hand, if you really want full simulation, we also have this other protocol that takes whatever factor super constant parameter you may allow and can give you a protocol of that round complexity and gives you negligibly close simulation. This is the standard notion of simulation and makes essentially the same assumptions. So some of the building blocks in a protocol are different, but really nothing much changes in terms of assumptions and of the properties. And again, now if you're comparing this with the classical setting and you're looking at things beyond constant rounds, this puts the post-quantum setting on even footing. And it's important to note that beyond the MPC and 2PC protocols I had pointed out earlier, there really were no attempts to reconcile these things. So, if you care about this particular branch of cryptography, you can now rest assured that we have the same sort of abilities in the post-quantum setting as well. By the way, all our protocols will have classical communication, which I guess I didn't stress as much before. So this is typically what is referred to as the setting of post-quantum cryptography, meaning that roughly your protocols behave in a classically compatible manner, whatever it means in a particular context, but give you security against post-quantum adversaries.
So just to make sure, this would mean
yes.
that all parties can be classical. The honest parties can be classical to run
Precisely.
the protocol, right? That's what okay.
That will become important in like a second because this admits the so-called LOCC setting, right? So a couple of interesting results have come out that build on ours.
So sorry, Rohit, could
Yes.
you before you go into the implications,
Yes.
could you please flash the slide with the previous results before yours?
Yes. I see.
The one before, no, just the. So this is the impossibility. There were also some constructions, right, that you had shown.
So these are, I think I've mentioned, but this will be GLSV 21 and things like that. I can like make a list and send you these things. These are interesting protocols. Like they follow known pathways as well.
But they were the main thing was these were non-black box, right? That's what you were saying.
Yeah. In particular, this
the key
closest
difference.
comparison thing was non-black box, yes. And
I see.
It turns out that this is because these are such highly interactive protocols with like a lot of moving parts, the black box thing really becomes a constraint in some sense.
Right,
so if you in some sense you can worry about the theory without really caring about the black box nature, but in some settings it becomes important. So I think the applications can nicely illustrate this point. So there's this result.
And sorry. Oh, one small thing just before we go on. So we have an impossibility result, right? That in constant round you cannot do it unless NP is in BQP.
Correct.
And so you essentially have both things. You're saying that in constant round, since you cannot have the best, you can't have perfect security, you get epsilon security, and if you allow polynomially many rounds of interaction, you also get or neglect like the standard notion of security. Right? That's the so it's essentially the best one can do, right?
Yeah.
Oh, right. Slightly super constant, you're saying.
Yeah. So you can do like log rounds and stuff like that. It just has to be increasing. Yeah.
I see. So it's there's nothing really left, right? Like it seems optimal in all senses, or is it like the message complexity somehow like is there anything else that people worry about that you think?
Message complexity you can worry about. I think it's hard to do better with the set of assumptions that we're doing, because if you're aiming for succinctness and things like that, right? MPC is very general. So for every functionality, it's usually like, this will take a lot of doing. And plus, these things are often heavily non-black box and things like that. So you will have new challenges of their own. So I think, I expect this to be a very hard problem.
I see. And except for perhaps UC security, I guess everything else is sort of settled with your work. In terms of.
I will note that there is some quantum UC model that was proposed by Unru. But it's a quantum and it's UC, so it's hard to work with. And I'm not sure if there's already a lot of people studying UC protocols in the post-quantum setting, but that would be Yeah, I mean, the nice
This-
thing is this is really also building on the classical pipelines towards these protocols.
Right,
So
right.
there's not really any natural barriers against maybe like the improvements we have done, like modular the techniques. We know some techniques just do not carry over into the quantum world with rewinding, things like
Mhm,
that, right? But
mhm,
there may
mhm,
be other protocol design approaches that maybe do not, sort of min-max on sort of rewinding and things like that, that may still carry over.
mhm,
And that is
mhm,
encouraging to me. You may be able to build other things that are also naturally nice.
mhm, mhm.
Yeah.
Got it.
Okay. Yeah. Cool. So yeah. So the first implication I wanted to highlight is this result by Kretschmer, Qian, and Avishai Tal from 2025, and they are building on this existing pipeline of works, which construct like these oracle separations that show you things in microcrypt essentially, right? So they managed to construct a classical oracle that shows the in with respect to which P is not equal to NP, but still somehow you have trapdoor one-way functions. I think in the standard sense, which is very, very interesting. It's a fantastic result. But because we now have this black box MPC protocol, this also implies the following corollary, where you can have a classical oracle for which P is not equal to MP, but you can still get MPC. And this is enabled, this is our super constant round protocol, which gives you full simulation. And it's enabled by the classical nature, exactly the property that, honest parties just have to run classically. And they don't have to do any quantum work, which you can essentially recover all the things you need to build the MPC protocol with trapdoor one-way functions. So that's one result. The result that uses our work in a non-trivial sense is this work by Bostanci and others from 2024. And this is sort of carrying over this well-known classical result that shows that if you have if you have arguments and cryptography, often you cannot expect a parallel repetition to work. So in particular, they show that for every possible polynomial, you can construct a particular constant round interactive protocol that is an argument system. That is, it does not allow you to prove false statements with more than a certain probability. But also the soundness will not go down with k parallel repetitions of the protocol, like you would expect it to with parallel repetition. And yeah, in the classical case, this is work from 2010s, 2015-ish, maybe by Rafael Paz, Chung, and others. And it's very, very interesting that the same result also holds in the post-quantum setting, right? And as in the classical case, this will also rely on this object that we will build called a non-malleable commitment. And yeah, so it shows that, apart from the question of MPC itself, these results may appear surprisingly in other places. So yeah,
Sorry, Rohit, I sort of missed a bit. So how do you see this result as a consequence of your result?
so this building block that we will build, that actually most of my talk will be about this non-malleable commitment.
Oh,
And
so this building block implies this result you're saying, not
yes,
the entire MPC. Okay.
not the whole MPC thing. Yes.
Okay.
Yeah. So yeah, that's why. Okay, so this is our definitions, results, and so on. So if there's no further questions, I'm going to start talking about our construction and things like that. So just to talk about our closest point of comparison, the ABG plus protocol that we mentioned before uses the following pathway to build MPC. So they're going to construct a sub-protocol that does multi-party secure coin tossing. And this is where they require the heavy hammer of multi-key FHE. And once you have that, it turns out that you can actually take certain two-round protocols from the classical setting that just use a CRS and then realize an MPC protocol out of it. And the CRS this is highly non-trivial. but it's already known. The way you use coin tossing is to just simply sample a CRS that all of the parties can refer to. So that's the approach. It's pretty clear cut. We are going to use, however, something that's drastically different, and that comes from existing black box MPC literature. So the first step will be to construct this post-quantum non-malleable commitments that I just mentioned. And then we need a particular strengthening of this called one-many non-malleable commitments, which sort of plays a part in a parallel setting. I will get into this later on. If you have this one-many non-malleable commitment and you have a malicious sender secure OT in the post-quantum world, you can realize what is a parallel simulatable OT. Because of the constraints I mentioned earlier, this is going to be just epsilon simulatable in the constant round setting. But regardless, you can then, this is really the clincher, because you can then take this sort of information theoretic compiler, meaning that this compiler makes no additional assumptions, and this is the part that's UZ secure. And if you have this parallel secure OT and you use this compiler, you will realize post-quantum black box epsilon MPC in constant rounds. And so this is clearly the pathway for our constant round epsilon secure protocol. The other protocol has a slightly different pathway, which I will not cover due to the interest of time. Yeah, so I mean, obviously this is very specialized, so I'm just going to describe more of the building blocks, and you will see how things build up from there. So yeah, so let's turn to this sort of crucial central thing in MPC design, constant round MPC design. You see these non-malleable commitments everywhere. So what are they? The necessity for them is the observation that you can sort of have man-in-the-middle attacks that standard commitments don't permit. So suppose you're playing correspondence chess, like people used to do 50 years ago. So you have a chessboard, and you play with your friends by sending them letters with your moves. And so, you may get a certain move, but suppose you were making money off of chess. The thing to do there would be to set up correspondence chess games with two different people. And let's say you go white in one and black in the other. So suppose one person sends you their move, you can sort of, given your choice of initial move, you can just start copying their moves. And so you send one person's moves to the other party replies with the response, you forward them to the first one, and depending on whoever is the better player, you will win at least one game. So hopefully you make some money. So really, this is breaking down because I'm able to relate the different commitments. So basically here the envelope captures the cryptographic notion of a commitment where I can't really see the moves, right? But that does nothing to my ability to like just send on these moves as if they were mine. So really the property that would protect against this is sort of an independence of my outgoing commitments from the incoming ones that I receive. And this is the security property that I really want. And it's crucial to note that this is not implied by hiding, right? Like hiding for the commitment really does nothing to doing this sort of man-in-the-middle attack. And in particular, if you have a homomorphic commitment scheme that will explicitly allow like even worse variants of such attacks, where you just don't directly forward out someone's moves, but you can make changes. So consider the setting of things like auctions, for example, right? If you have an auction and somehow you were able to bid after seeing other people's bids, suppose these bids are in the forms of commitments, if the commitment is homomorphic, you can just take someone's bid and sort of, amend it. And without knowing the value of the other person's bid, you can just make your bid a little bit higher and so win the auction. So this is really some sort of a very independent security property that does not come up for standard commitments. And it arises very naturally in the sort of man-in-the-middle settings. So let's build some notation for this. So what is this man-in-the-middle attack? So I call this execution the man-in-the-middle execution, where this middle party, yeah.
But before you go on, just a small question. So does authentication not solve something like this? If you like
The authentication will,
or like signatures or something like that, doesn't fix it immediately. this. I'm guessing there's something more subtle happening, but I don't see why this
I see.
naive
You're
approach
saying,
doesn't
okay,
work.
so even if you sign, right, the copying attack might still work because, if you communicate your public key credentials and things like, okay, so you're saying, suppose everybody has different public keys.
Yeah.
I
So
need to
everyone
sign
has
with respect to the
broadcasted.
message.
Yeah. So
Yeah,
even
so
if like the man in the middle forwards it, I mean, they would not pay out to the man in the middle, right? They would only
so
pay to the original party. I would have
in that
thought.
scenario, actually hiding becomes the sort of the obstacle because if you're signing, you can't sign with respect to the message in plain text, right? Because that will reveal things. So really you have to sign with respect
Oh,
to the commitment, and that is kind of the layer you have to fight with. You can't, authenticate things within the commitment without compromising secrecy of the message.
hmm, I see. And if you do it on top of the commitment, then I guess there are issues
Then you
because
can copy again. Yeah.
I see.
Yeah. So as it turns out, this copying is something we won't be able to do much against, but I'll get into it in just a second. So again, so this is the setting that I have. So there's a committed with a certain message of its choice in what I call sort of the left-hand session. And there's a receiver on the right to which I am playing as the committer. I'm going to define this random variable, which is called the MIM random variable. And this is going to consist of the man in the middle's view, meaning what it sees in the protocol execution and its own randomness and things like that. And in particular, it's going to also have the message that it commits to on the right. So note that the public view of the protocol does not actually tell you what is committed because what I'm going to commit is going to be hidden in the commitment. So you have to add this right word committed value, which we call m tilde, explicitly into this random variable. Yeah, so you're taking these two things. So this will enable us to talk about the security property that we want. So like I said, this does not necessarily stop copying attacks. So to guard against such things semantically, we insist on this tag-based notion of commitment. So each, in sort of correspondence with a signature, you're going to sort of tag each particular execution of such a commitment. And so now my security requirement is going to be with respect to the condition that the tag on the left-hand session is different from the tag on the right-hand session. So let's turn to the definition. So you have the man in the middle execution from before, you have the random variable, which
Rohit,
is this. Yes.
so why are we using m tilde instead of m if we are adding it by hand? Oh, it's supposed to be the value committed by the
So
party on
by,
the left, right?
yes, but m tilde may not just be m, right? It could be something that depends on m. And I don't want to allow for that dependency also.
But you're adding it by hand, so what do I think? How do I add m tilde if it's not even? Is it a message produced by one of the parties? No,
You're
I'm
saying, can you
confused.
efficiently, oh, it's produced by capital M.
So capital M also produces m tilde in addition to the view, and the view is public, you're saying, but it doesn't reveal m tilde, and you're just allowing it to
Correct.
produce m tilde actually. Okay, got it.
Yeah,
Sorry.
so it turns out to define security in an operational sense, you need this m tilde,
Right.
and you won't get it from view. So that's why I do
Okay.
all this.
I see.
Yeah.
Thanks.
Okay, so what am I going to expect for the security definition? It's going to look something like this. So if my right-hand side is going to be independent of the left-hand side commitment. Oh, the arrows are slightly wrong, but yeah, don't worry about it. Then I want the property that no matter what someone commits on the left, the thing that I commit to on the right is independent of that. So one particular way of describing that is to say that if I commit to two different messages on the left, the man in the middle is not really going to be able to change the distribution of its own committed value, which is m tilde, right? So in particular, this MIM random variable is going to look computationally indistinguishable in both cases. Like I said, I can just copy from the left to the right, and then this guarantee would be broken. So this is why I need tags. So I'm going to have the condition that the tag on the left is not the tag on the right. And then this definition makes sense. I'm just gonna give it a second. So people absorb this.
So of course you can just copy and forward it. So you could make t tilde equals t, but
I reject that. So if I'm if I'm the security
so who's the
challenger,
I?
in this context, I was saying as the security challenger.
So somehow that notion is going to be useful in some operational sense, which we'll see later, I guess. Okay.
Kind of, maybe not too much, but yeah. Yeah, so you're submitting these tuples. There's basically these MIM variables to some challenger. The challenger will essentially run both C and R, so to speak, and then you will judge whether you won or not, depending on V1. And there's some subtlety hidden here, which we'll get to soon. So let's give some. Yes.
Sorry, just
Yes. I think you see it.
So no, I don't think I'm saying anything non-trivial. I was just trying to see in this context, like, or just thinking in terms of the chess thing that you were saying earlier. Before they decide who gets, who wins, they could probably broadcast the entire transcript, including the tags, right? And then you're checking if the tags are consistent, then the man in the middle doesn't get it. No, but then the man in the middle could have forwarded it.
No, that's precisely the issue. So the point is, you don't know M tilde from all the public information.
Yeah, you don't know M tilde.
So
that is correct.
So in the game, I'm going to be simply given M tilde to check. So this is an inefficient step. So I can always take the view, break the commitments, and obtain M tilde. But you don't kind of care because the context of the security game that you define says that someone is going to come and give you M tilde. And M tilde is a well-defined quantity because the commitment is statistically binding and so on. But if you're trying to check this condition on your own efficiently, you can't really. And this is going to be become relevant several times.
Okay. Yeah, I'm not able to fully appreciate the intuition yet, but I guess you'll explain.
I'll try. Yeah. Okay. Cool. So let's see why this is an interesting object and why you can't simply build it with commitments and some clever ideas. So this should be fun. So let's see. So I take commitments. Prove in lieu of your signature idea, right? Let's say I prove that I know the value I committed to. And in principle, this should be hard for the man in the middle because it does not know if it's like just copying or if it's just making some edit to the commitment itself, not to the message underneath, but the commitment itself. It does not know what message it is committing to. So hopefully the zero knowledge property guards me against this. But you can't prove security of this. Remember that the security challenge will give you M tilde, but if you're trying to design a reduction, the reduction really has no way from participating in this protocol to get the value M tilde. So you have defined the security requirement, but there's no way of enforcing it. So this attempt doesn't work. So let's try something slightly different. We have things called proofs of knowledge from which you can extract things, right? So instead of just using a zero knowledge proof, I use a proof of knowledge. And now the ability I gain here is that on the right, if I am the reduction that's running against this middle adversary, I can try and extract the value M tilde. But then you run into an issue because as soon as you try and extract M tilde on the right, the privacy of your proof of knowledge on the left is no longer clear. Because if you're rewinding on the right, these two messages, basically, these two zero knowledge executions are sort of, you cannot rewind one without rewinding the left-hand side also. And your zero knowledge property is not defined with respect to rewinding unless you use a specialized protocol. So now the man in the middle might very well know the message you're proving knowledge of. So there's no way to simulate the left interaction. And again, you have a problem.
Oh, I'm sorry,
So
sorry. Could you say that again? I didn't fully understand. So
yes,
you said that the man in the middle will know M.
yeah, that's hard to make because
Why?
the man in the middle may not know M. Like you cannot prove that the man in the middle knows M just because I'm rewinding on the right. But you can't also prove that M is hidden in a zero knowledge sense anymore. Because formally, because the zero knowledge requirement
It's a
is no
proof
longer
of
applicable.
knowledge.
Yes, so like if to say that the man in the middle can definitely extract M involves making an assumption on how it behaves, but you cannot argue secrecy of the value M anymore. So by now, I think we have established that you're doing something slightly subtle to account for this. You want to sort of hide things, hide your own committed message on the left, but you want to reveal it on the right. So how can we do this? So we have some amended template.
Rohit,
So
sorry,
we may try, yeah,
sorry, I'm being a bit slow,
no,
but
please.
I'm not fully sure I understood the. So if you have a zero knowledge proof of knowledge, right?
Yes,
The receiver does not learn M, right? Unless, of course, it rewinds
yes.
the prover. So when you run an instance, the first zero knowledge proof of knowledge,
Mhm.
why can't we just argue using the fact that it's a zero knowledge? It's zero knowledge, so the man in the middle, and since the man in the middle cannot in an actual protocol rewind, it could
Yeah,
not
but
possibly.
you
Oh, but you're
want to
saying
argue
that the second.
that might still well be true. Yeah, so the issue is my reduction cannot enact such a scenario because my reduction will need to rewind the right
I
hand
see,
side.
I see.
Yes. So
So
in
so
the
your
context
reduction
of
would
this
have to
reduction,
rewind
yes,
sorry,
the
sorry,
right
please
hand
go
side
on.
proof. Yeah.
Uh-huh.
And as soon as I rewind on the right, my left execution is getting rewound also. I don't know how to stop that.
I see, I see. So because
Yeah.
you're extracting it from the man in the middle, so you have to
Yes.
rewind that as well, and then once you start rewinding, then the zero knowledge property no longer applies. Is
Yes.
that what you were saying? Okay,
Precisely.
okay, okay, okay.
Yes.
Sorry. Okay, sorry, I'm a bit
Yeah.
slow, but okay, thanks.
No, no, no. I mean, I drew out these examples because, yeah, usually nobody does them, and then things seem way simpler than they are. So, okay. So I think I've communicated some of why this is hard. So what I'm trying to do is we have interactive protocols, so we can do some more setup with them. So instead, I'm going to have some sort of secret based on the tag, because remember that the tags are different in both instances, and maybe I can exploit that asymmetry. And so maybe I can do that again. And so I have this middle block of communication where I'm proving some secret based on the tag value. Um, and then the goal would be, suppose the zero knowledge protocol is also amended to sort of make use of this secret. Then my hope would be to basically follow the same strategy as earlier. I just rewind on the right to get some value. But now I'm hoping that this setup that I've done helps me get around this rewinding on the left-hand side in some way. And observe that this will get us much closer to proving security, because if I can argue that uh, the view plus this value v tilde that I extract on the right is computation indistinguishable, then I can argue that the original non-malleability guarantee holds if this extracted value is going to be the message on the right with good probability. So it doesn't need to be probability one. If I can argue this in some significant fraction of cases, I'm good. So there's still gaps here. Yeah, I know this is already a lot of stuff. So yeah, just please take a second.
Mhm. So how do I think about V tilde? So it's an output that is, so it's in the same
Yes,
spirit as producing M tilde, is it?
it is in the
That's
same
the,
spirit, but yeah, like I suggested, I will have to widen my zero knowledge proof. So maybe I'm going to prove something like uh, I know M tilde, or I know the secret that was shared from the other party. So if I do that, now this v tilde can be one of two things. It can be either the message or it can be the secret. So it's not necessarily the message anymore.
So why can't, okay, so a dumb naive question, why can't I just forget, like as the man in the middle, why can't I just neglect the secret based on T and T tilde altogether and just focus on extracting M?
Yes, so
Yeah.
then if you try and extract M, and if I'm proving this more general zero knowledge statement,
Oh,
the
okay,
zero
okay. So
knowledge
maybe so zero knowledge statements are, you're saying it's not just I know M, it's like I know M and something about T, is
yes,
that?
precisely.
Oh, okay,
We'll
okay.
see
So
it
okay, okay. So
explicitly. Yeah,
something has to depend on T. Okay, okay. That's what I mean.
yes,
Okay.
yes. Okay. Yeah. So yeah, this is what we are going to try and do. So more generally, this is what is called the challenge of robust simulatable extraction. And we'll see what robustness means in a second. Because and simulatable extraction is because we are both simulating these sessions and extracting the committed value by M. So we want to prove this property. And so roughly in our approaches, we have seen so far that there's this extractable gadget, right? That we can sort of exploit to get the committed value from the man in the middle. And there's also a hiding gadget, which is essential so that the man in the middle just doesn't turn around and start extracting from the left session. And the hiding part typically should not be touched, but the extractable gadget is going to be rewound, right? But of course, you can have more general man-in-the-middle adversaries that just schedule things in a weird fashion, so that when you try to extract from the green part on the right, now suddenly you're touching the red part on the left, which is very unideal. That will again break security. So even the stuff we described in a previous slide will not necessarily be enough. And you can get around this. And this is essentially what the constant round MPC protocols had to do. And what you do is usually you introduce more rewinding opportunities or pockets where you can rewind from in a way such that when you argue security, the adversary is not able to do that as well. You can do complexity leveraging, which means that you just use different layers of security of your cryptographic primitives to enable things. And this will give you basically the thing that you want. But of course, the challenge is doing this in the post-quantum setting. Okay. So what can't we do in the post-quantum setting? We can't rewind classically. So this is to, yeah, and some mention should be made of related work which are solving similar problems, which includes the 2PC works that I cited before and some related work as well. The reason that we cannot use the previous strategies is now rewindings are not that simple. You cannot just reset the state of a machine and sort of, run it multiple times. This is now a coherent operation. And also, you cannot do the crucial thing in rewinding, which is like looking at the answers from each particular rewind, because you cannot necessarily measure the intermediate transcripts, or you will end up destroying the execution. So this is a well-defined and a fairly hard problem to solve. Okay, so what do existing non-malleable commitments do? What do we know about them, rather? So in line with what we know about the MPC protocols and
Sorry,
yes,
sorry for the interruption.
Mhm.
Also, if I'm interrupting too much, just tell me, and
No,
and
I'm
if
happy with, yeah.
okay. So what was known about the two-party setting? I think you mentioned it, but I sort of forgot. So basically, I wanted to understand why the two-party setting, the two-party. Okay, I'm guessing that in the for the case of two-party computation, it is the post-quantum security was known. Right? Like, it's like one of those DNS. I forget. Like
Yes,
it
yeah,
was known, but that doesn't work in the MPC setting. I'm guessing. So
correct.
I didn't understand how do they solve these problems? Because what you're describing seems to just be also apply to the bipartite setting, right? or the two parties
Yes and
settling,
no. So
where's
basically,
the difference?
the point is the way you use this non-malleable commitment is really when you have three parties or more, because you will receive certain information from one party and maybe you need to send certain information in your own stead to the other, right? In the two-party
Oh, so
setting,
there's no
this,
man in the middle
yes,
really, in a sense, I see, because there's no
yes.
middle.
So you
Oh,
don't
okay.
end up needing non-malleable commitment. Yeah.
I see. I see. And what was the connection? Have you so far stated the connection between non-malleable commitments and this man in the middle thing? Or you're going to it?
In the context of MPC, right? Yeah, I'm not going to touch on that. But yeah, it's roughly in the sense I suggested. Like, you know, you need, if you have man-in-the-middle attacks within the context of an MPC protocol, then you can't really show security because, you know, then in an intuitive sense, suppose you're cheating and you don't really have an input of your own in the MPC protocol and you start doing these man-in-the-middle attacks, then you can just sort of complete the execution without your own private input and things like that.
Mhm. So, but what
So
was the stuff you were describing with the green the green and the red rectangle? Uh,
oh, this this
is
this
that not related to the? I thought so. Non-malleable interactions are going to solve this problem, or is it something else? I think I'm sorry, I'm getting a bit confused.
yes, so I
This
guess maybe
extractable
this
gadget.
is also more confusing than I intended it to. So this is one setting where you can have this sort of problem of robust simulatable extraction, but it's not limited to non-malleability necessarily. So the left and the right things arises very naturally in non-malleability, but um, even in a 2PC setting, you can have things like where you are trying to rewind something, but because of scheduling, you are not able to, and things like that. So it arises for other primitives as well, is I guess the point here.
Yeah. Um,
And I think
so
I also meant this in a more general sense than just this left and right sessions. Yeah.
okay, okay. So non-malleable commitments are basically able to implement this green-red idea. Is that
Yeah, I
the way to
guess
think about it?
the point is, yeah, so to build a non-malleable commitment, which is a subset of building other sorts of yeah,
Robust,
interactive primitives,
robust.
you need to solve this
Mhm.
challenge.
I see, I see. Okay.
Yeah, so
So
it's
that's
in some
one
sense more
primitive in
generic.
which you solve it. I see. Okay, got
Yes.
it.
Yeah, yeah, yeah.
Okay.
So okay, so yeah, so the known line of work for non-malleable commitments classically is you had the initial construction by Dolev, Dwork, Nauer. You had constant round constructions from CRHFs in the mid 2000s, and like I said, there's constant round constructions from one-way functions now. Yeah, I think yeah, you're missing OT in the MPC construction because the non-malleable construction just needs one-way functions, and that is true still in the post-quantum setting. In the post-quantum setting, what we know about such commitments is by way of building the MPC, you can build this non-malleable commitment using the same non-black box assumption. Sorry, the assumption is not non-black box, using the same hardness assumption and non-black box techniques from ABG plus 21. And otherwise, also, other people have been working on this to get super constant round constructions from post-quantum one-way functions.
So, so
And
just to
these, yeah.
quickly check, so if we can have, so basically all of this is used to instantiate the common reference string model. Is that
For ABG
correct?
plus, yes. For the other two works, this is not correct.
So they do something else. Okay.
Yes, yes. They use basically some, yeah, introducing extra extraction opportunities kind of method, which is why it's not constant round. And really, this
And
is
not,
going to be one.
sorry, please continue.
Yeah, so I was just saying that this is going to be one of the big jumps, really, in constructing these things. But what were you saying?
Well, I was going to ask that the non-malleable commitments by themselves do not imply OT, right? Because
Correct, correct, correct. Yeah, so that is definitely
so
true.
you need some extra. Okay.
Yes, yes, yes. Okay, so some terminology is useful. So this is because the things I'm going to illustrate, the toy case is going to have these things as conditions. So by small tags, I mean tags are in this polynomial size range. Typically, you want to allow exponentially many tags because you don't want to limit number of sessions and things like that. One-sided setting means the tag on the left is going to be smaller than the tag on the right. And I also have some conditions on the protocol, which is synchronous means you are scheduling such that every message just goes as is indicated in the diagram, and any other sort of scheduling would be asynchronous. And if this is too much terminology, just ignore these things. It's not going to matter much going forward. Okay, so really a crucial work happened in the work of my co-authors that instantiated a constant round non-malleable commitment. So how does this work? The protocol looks as follows. Sorry, yeah. There's going to be an initial standard commitment to the message. Then the receiver is going to send a hard puzzle with, let's say, T solutions. And this is important to know. This has exactly T solution, and each solution is sort of independent. Then the receiver itself is going to give a proof of knowledge to the effect that it knows one of the solutions to the puzzle. The sender is then going to generate a proof of knowledge of its own, where it shows that following the template we described before, it knows the message that it committed to in the first round, or it knows one solution to the puzzle. And in the man in the middle setting, this is just going to look like this. And note that we are sort of following the convention that the tag on the right is larger than the tag on the left. So the hard puzzle step will generate a hard puzzle with different number of solutions on the right and the left.
So I guess you're assuming that it's easy to sample a hard puzzle and one
Yes.
solution to the puzzle, right?
Yes.
And it's hard to find.
And yeah, if this is arcane, just let's say you sample like k one-way function images or something, T many one-way function images or something, that will usually work. Okay,
but so then you could potentially know solution to all of them. Is that what you're saying? It's not.
Yes. So this is just the thing to note here is the receiver may know solutions to the puzzles, but in this structure, the sender will just see the puzzle, right?
The sender.
It didn't come up with
Who's
the
the
puzzle
sender
itself.
and who's the?
So C, for example, yeah, if you look at the
C is the
left side
sender
thing,
you're thinking.
C is the sender. So C will just see the description. Yes, exactly. And really, the only thing that's going to be true is that you will have to rewind in this proof to know a solution, and that is what we are going to exploit. Right. So
it's not clear to me yet why T plays a role here, but I guess you'll tell us.
You'll see in a second. Yeah, that's the cute part of this protocol. So okay, so to simplify things, I'm going to.
Sorry. Also, sorry. One last question before you go on. So we're going to somehow, since there's no way for C to actually solve the puzzle, it's not clear to me why in this second proof of knowledge we're requiring either of those things to be true, which I guess also you will explain. Is there like some simple way of thinking about it before we go to the details?
So I have just set up the template I set up before. So I have this thing, and it's going to be very unlikely.
I didn't understand it then either. That's what I was saying.
Sure. Okay. Yeah. So all you're doing is really setting up this. It's saying that unless this very unlikely event happens, I am just going to be proving knowledge of M, right? But in the course of the reduction, what you're going to set up is you're going to sort of uncover this solution, right? And then you're going to use it in the proof that follows. So now you're sort of able to cheat. Correct.
So you're going to rewind the first proof of knowledge? Is that what you're saying?
Yes, and you will see why this does not help the man in the middle in the next slide. Yeah. Because you're right, you're sensing that the man in the middle can do the same thing, right? So what's stopping it? So that will require some arguing. Okay. So I'm just going to talk about view 0 and view 1 to distinguish the cases where the committer on the left uses M0 or M1. So let's look at it. So how will I sort of argue that view 0 is similar to view 1? I want to rely on the hiding of this initial commitment. And towards that, I will build a reduction that takes away the whole setup of this interactive protocol with these two sessions. And I just want to look at the commitment on the left initially as one thing and the entirety of the protocol as another thing that happens inside my reduction. And this is going to, the reduction is going to give me an adversary against the hiding of the commitment. So what I want to do is, like we have said before, I want to extract the proof on the right, the committer's proof on the right, to get this value v tilde. V tilde I want to ensure is usually m tilde with good probability. It can also be a puzzle solution. So how do I ensure this? Right, this is just saying what I said.
Wouldn't that immediately break the hardness of the puzzle if it was the solution to a puzzle with non-negligible probability?
Yes, you will use that in some form, but not quite directly because I set up the puzzle on the right? So that's not breaking anything yet.
Oh, that is true. Okay, good. Yeah, thanks.
Yeah. So, okay, so you're extracting this, and now, as you pointed out before, the man in the middle may do the same thing on the left. So you cannot really use the message M. That will not really reduce to hiding. So I'm going to do what I said. I'm going to extract this puzzle solution from Vipok-1 on the left. And I'm going to use it. This just means that I can do what you were alluding to before, which means that the M can start doing that, doing the same thing, extracting from Vipok-1 on the right and then committing to the value. So now V tilde is not equal to M tilde anymore. And note here that the secrecy condition of Vipok-2 here does not help because, again, I'm rewinding. And this has no non-malleability guarantees as such, right? If I'm rewinding, all my secrecy is lost, so I can't really rely on the secrecy. So I want to do this unfair thing where I want to cheat in this sense. I want to rewind from Vipok-1 and then use the solution in Vipok-2, but I want to disallow M from doing this. So now I am going to exploit the fact that this T tilde on the right is larger than T on the left. So the solutions that are usable in Vipok-1 are x1 tilde to x3 tilde, let's say. And this is one set. The solutions I can use on the left are a smaller set. And now there's some pigeonhole kind of phenomenon that's going on, which is to say that there exists an xk, and there exists two distinct xi tilde, xj tilde, such that if I use xi tilde or xj tilde in my Vipok-1 on the right, the adversary uses the same xk on the left. And consider the following. Suppose I was given this xk, and suppose I wasn't rewinding the Vipok-1 for the moment. I have the phenomenon that when xi tilde is used on the right, xk is used on the left, v tilde is going to be m tilde or xi tilde, right? And similarly, when xj tilde is used on the right and xk is used on the left, v tilde can be one of the message or xj tilde. But assume for the moment that the reduction magically knows these xk, xi tilde, xj tilde for the moment. This means that really v tilde now has to be m tilde. Because in this scenario, that's just on the slide, forget about the rewinding I was doing before. I'm not rewinding Vipok-2 at the moment. So by the secrecy of Vipok-2 on the right, V tilde really has to be M tilde. Does that make sense?
Okay, I'm a little bit lost. So let's look at point 2 again. So when xi tilde in Right.
So because there's just simply less solutions to the left puzzle than the right puzzle,
Yeah.
as a probabilistic
So
system, I'm going to have this event where for two particular solutions, xi tilde, xj tilde on the right, M
mhm,
really has to use the same solution on the left.
mhm,
And if this happens,
mhm,
then really it cannot change its answer in Vipok 2 on the right. It has to really still use M tilde because otherwise the reduction that I'm going to use to the security of Vipok is I'm going to switch between either xi tilde or xj tilde, and then I get V tilde on the right, right?
mhm,
So when I look at V tilde, if M is not using M tilde on the right, note that I'm no longer rewinding Vipok 1 to extract the solution. Suppose I'm given the solution magically. If I'm not rewinding Vipok 1, depending on whether I used xi tilde or xj tilde, the solution
mhm.
that I get by rewinding in Vipok 2 changes. So this is actually indirectly breaking security of Vipok 1.
Mm. So, hmm. So we're looking at M in isolation at the moment. The
Yes.
the reduction doesn't know the solutions explicitly, I guess. That's what.
Let's say it does even. Like it doesn't know all the solutions, but it knows this triple xk, xi tilde, xj tilde.
Um, so if it already knows it, then how is it breaking VPOC one?
Yeah. So we
Because
will turn to that because Vipok on the right, I know the solutions too. Vipok on the left, I
okay,
know this one particular solution, and but note that I am not looking at it. Like I know this value xk. Sorry, it's enough to know xi tilde, xj tilde, and know that there is such a k. You don't need xk. You're right. Otherwise, the deduction will not go through.
okay, I think I'll let you go on because yeah, I'll probably bother
Yeah,
you separately because I think I'm dragging everyone down and people are maybe
I see.
yeah,
see.
maybe
So
we
how
can
much time
continue.
do I have left?
Oh, you have time. I mean, you have. When
Okay,
did
okay.
we start? We started at 11. Oh yeah, it's about 12:30. Shoot. Yeah, okay. Let's maybe try to wrap it up. Yeah, sorry. I
Sure,
think I asked
sure,
too many
sure.
questions. Sorry. Mm,
No worries. So I'm gonna try and speed through them. So of course, this magical case will not happen all the time. So instead, you will have some more distributional flavor of this to do these things. So now one larger point is if you do this extraction business, classically this is fine, but in the quantum case, this is not going to be enough because you'll also need to preserve the state while you're extracting. But that you can do, and I will have more to say about this later on. So this is how this basic template works. Now, why is this non-black box? It's non-black box because I am proving things about this puzzle solutions. So it's non-black box in the puzzle system I set up. So I have to get around that. And also the VPOC is not necessarily itself itself black box. Typically, this is going to be non-black box. So I have to make sure that I use a flavor of VPOC that's like black box. So here's the challenges. The main one is that I am using the knowledge of the puzzles, and I'm also using the knowledge of the initial committed message. And this makes the second proof non-black box in the commitment protocol. So what do we know about black box proof systems? So really one tool that we are going to use is this idea of MPC in the head, which is really a way to perform black box MPC protocols. And this is going to use information theoretic MPC as a tool. So you're not really using any assumptions, which is good. And this basically it's this very cute idea where you take an MPC protocol and you take the views and sort of commit to them, and then the verifier can check some of these views corresponding to virtual parties that are in your head, and you reveal them, and this sort of gives you both zero knowledge and soundness. Well, we are going to rely on WI here, but both things work. Let's not dwell too much on this at the moment. This is a standard tool. And in fact, you can augment it. So when you do this black box zero knowledge protocol, you can also set it up to do this so-called commit and prove, where you can sort of commit to different values in this sort of MPC sense. And then you can perform further joint computation on them to reveal finally, actually to securely prove that a predicate over these committed values holds. So this is a more advanced functionality than previous. And it's carried through in roughly the same sense. So these were protocols that were established in the 2010s, and this is also a well-known standard tool. Finally, we are going to use extractable commitments, which are this idea of commitments where you have a committer that commits to a particular value, and there's some state at the end of it. And in a post-quantum sense, you can build this notion of an extractor that gives you this committed value. And the closeness is actually statistical, but you inherit some epsilon here. So we can use this extractable commitment to actually initialize the black box commit and prove protocol in the post-quantum setting. So now our new black box non-malleable commitment is going to look as follows. You will commit in some black box sense, in this sort of MPC view sense to something, and then you will have the same template of puzzle solutions, committing to the puzzle solutions in EXT-COM, and then proving that this is a valid solution, committing to some value in EXT-COM again, and now you would need to reveal the puzzle solutions due to a technical reason, and finally you prove something along the lines before. So now we do not have proofs of knowledge directly, but you're sort of using extractable commitments and a proof together to get essentially the same functionality. And this is compatible with black box commit and prove, and really the only extractability is coming from EXT-COM. So you're not using any standard non-black box tools. So you can instantiate this protocol in the black box manner. And all of these things are constant rounds. So our new black box protocol is also going to be constant rounds, which we wanted before. So you have to do several things to the hiding challenge and so on, introduces complications, which we are able to get around. Now, like I said, sort of our proof of knowledge has been split into this extractable commitment and the black box proof. This complicates the proof a little bit because it's much nicer to just use this one object for both purposes, for both secrecy and extractability. Some words about simulation extraction, which we haven't described before. You want to consider sort of the reduction earlier, which extracts some value, but it ends up destroying the state. And you can sort of use Jordan's lemma to look at the space of outcome, and you divide it according to some threshold. So you look at sort of the states that give you good success probability and give you bad success probability. For the good success probability case, you can sort of amplify your success value and then extract the value without damaging the state, which is good. For the bad success probability, you show that you can essentially ignore it if you set the threshold cleverly. And this is really the step where, because we can handle this threshold delta, this needs to be noticeable. And the runtime depends on 1 over delta. And since runtime is some polynomial, I can only fit in some noticeable delta. I cannot make delta negligible. And this is really where the epsilon requirement comes in. And there's some noisy business that we can do and so on. And just a couple of quick words about one-many non-malleable conversions, because I'm running out of time. This considers the setting where there's not just one write session, but multiple ones with different receivers. This becomes important in MPC because you're usually sending messages to multiple recipients. And it's analogous. Everything is analogous to the non-malleable standard non-malleable case, except you have different parties on the right. And Now we'll follow the same template to realize this one many commitment. The security arguments are going to look a little bit different, but not much is going to change. So basically, when the thing here is that now you're starting to, you want to extract the values, but the reason this becomes a problem with quantum extraction is, suppose you extract from one session on the right, you will get this value, but now you've destroyed the state to an extent. So the argument from before doesn't directly necessarily fly. So you have to use some other tools from this sort of extraction literature in the post-quantum setting. Use what is called quantum state restoration, which gives you some sort of operation you can perform. And then you basically alternate between extracting this value and doing this so-called state restoration multiple times. And you keep doing this across sessions. And this is enough to show security in the one many case. So you're going to extract using the same extractors as before. You're going to have this quantum state restoration step. And this is described by our so-called simultaneous extraction lemma. This will give you the parallel OT that I mentioned earlier to instantiate our template. And finally, we're going to use the well-known IPS compiler to take this parallel OT and get you black box constant on epsilon secure multi-party computation in the post-quantum setting. That's it. Yeah. Yeah, sorry, I had to rush at the end.
No, it was mostly my fault. I'm sorry, but yeah, thank you so much for the lovely talk. I guess I
thank
can
you.
clap on behalf of everyone. Okay, there's only 2 people left. So I don't know if they have any questions.
Can I ask something like I don't think if it is very relevant, but since you showed the man in the middle attack,
right?
Like, can we assume some Benjamin type of attack in distributed setting? And
consensus.
Yeah.
I see. There's usually in the protocols you're doing this distributed, so like it's not distribution computation in sort of distributed computation setting. You're usually taking like a bunch of secret shares and things like that and computing over them. So there's really usually no consensus problem I can see being set up necessarily. Every party just kind of takes in messages, kind of does its own thing, and then contributes. I guess if you're doing MPC for a consensus problem, then maybe something can be possible, but I'm not sure. Typically, we don't look at consensus problems here. Yeah.
If you look at it, do you think we will get any advantage over classical? In classical, what we do is we just repeat the broadcast in any agreement or consensus problem to get eventually to correct answer.
Right.
And like, if we use the stacks or whatever, I did not follow correct exactly, but like,
I see.
What you're doing, man in the middle,
Yeah,
like
no. These like the non-malleable commitment is not really getting you any additional benefit in terms of communicating information, right? It just sort of gives you this hiding and this non-malleability property. To agree on it, like you can imagine that you take any particular consensus protocol and just transmit messages using non-malleable commitments in each step. It doesn't seem to really change the underlying problem of the consensus itself, right?
Yeah.
So maybe I'm not sure if that can be done.
Yeah. Thank you.
Yeah.
All right, then thank you so much, Rohit, for the lovely talk. I think this deserves like multiple talks. I don't think I could.
Yes, thank you everyone for attending. Yes, and I hope to see you guys around.